Welcome everyone to our session. This is a double topic. If we had time, I would probably cover both of them, but as I told, it's planned for 2 consecutive weeks. So I think that we will talk about behavior patterns next week. Autonomous agents. First of all, where we are in our model of AI, decision-making, movement, character AI, strategy. You know this diagram from the last week and from 2 weeks ago. Last week we did decision-making. So last week we were here, okay, with our decision trees and state graphs, state machines. Today, we will be mostly looking into movement. All right, movement is very closely coupled with decision making because in order to move anywhere, you have to make a decision to move. But also without some kind of information, orientation in the space that surrounds you, any decision making about possible movements, if not well informed, will be ineffective, okay? So we will be looking, first of all, what to do to recognize what's around you and how to plan your movement. And here we arrive to a very important aspect of AI, which is called autonomous agents. What is an autonomous agent? For gamers, for game developers, autonomous agent is nearly the same thing as NPC, so non-player character. It's some kind of entity that has onboard AI. But what does it mean that it has onboard AI? First of all, it senses the environment. It doesn't necessarily mean that it has eyes, nose, and ears, okay? But it has some way to control what's around, okay? What is the agent's environment? It can also, it has capacity to act upon this environment, so perform actions that will change the state of the environment. And it can also act in order to pursue its own goals, okay? So agent is something that has a goal to do something. For example, this goal may be to kill the player, to guard some area, okay? To not let people in or not let people out. So these autonomous agents currently discussed by friends over there can act in pursuit of their own goals, and this means that they can somehow change the environment in order to achieve their goal. Okay, and that's the central thing about agents. All right, we decided that agents have to sense the environment. Sensing the environment is known as perception, okay? Perception is a term used in psychology, but also perception is a term used in AI. All right, so what does agent know? And this is a very important question because very much unlike biological structures, agents do not have senses in the same sense as we do. Okay, they don't look at the world through their eyes. They probably get information about the structure of the environment through some kind of a database. All right, so they can access world information directly, and this means that perception system of autonomous agents have to be carefully balanced. If it is not balanced, we can have one of 2 situations. If agent has insufficient information about environment, it will be stupid, okay? An example of a stupid agent,
I'm in a meeting right now.
Okay? And the agent ignores this danger, okay? And eventually gets killed because he ignored the guy entering the room with a gun, okay? Agent thought, oh, never mind. And in a moment it's killed, okay? But lack of balance can also mean excess of information or omniscient agents or simply cheating agents, okay? Cheating agent is an agent who gets the knowledge that it should not normally get. So an agent in a similar situation in the real world couldn't know that. So an example is agents who can see through the walls, okay? Unless seeing through the walls is an element of the game. If a agent is a ghost, okay, I assume it might see through the walls. But if the agent is a soldier, guard, and something happens on the other side of the wall, and the guard knows about it and runs there, that's cheating, okay? So what the agent can see, what the agent can remember, because these are the two different aspects. It's not only about what the agent at the given moment. The agent can have also some knowledge about the past. And an example of a stupid agent without any memory. Imagine that an agent, an enemy, is chasing you in a game, right? And you run over a corner, disappear from the direct sight of the agent, and in that moment, in that very moment, the enemy stops, completely disoriented. That's about you. Okay, it's everything I can see. I can see the player, right? So when you turn around the corner, at least what the agent should do is to store the information where you disappeared and follow the most likely direction in which you ran. Okay, but on the other hand, if you did some maneuver, turned unexpectedly, okay, and you are still behind an obstacle, so the enemy shouldn't know where you are, but the enemy abruptly turns and charges exactly in the direction you are. It's probably cheating. So agents can see objects in their neighborhood, hear sounds, react to collisions, understand speech, okay? But you have always to remember about limitations of the knowledge that agent can have. I showed this diagram 2 weeks ago, so it's just a reminder. But if we have a player inside the room and the enemy outside the room, then there is the area of visual awareness, which is cut off by the wall. I assume that the wall is not transparent, it's a solid wall. But audio awareness is broader, okay? You can hear things through the walls. And of course, this builds exciting opportunities for a game designer because the player can now hide inside the room. And if it is silent, it won't be spotted by the enemy. But if the player does anything that generates noise, it will be immediately spotted and perhaps attacked. Okay, another question here would be if the enemy can hear the player, how can he attack without seeing the enemy? Sorry, without seeing the player? It's reasonably easy because it can detect the direction where the player is from listening to this noise, okay? But then how he or she is supposed to maneuver, find the door, and get to the player if it is not a straight line, okay? But this will be discussed in 2 weeks' time when we will be discussing pathfinding algorithms. Okay, so we will know what the agent should do if the route between the agent and its destination is, well, complicated. All right? So today we just assume it will find a way and it will attack the player. All right. This kind of AI is the basis for game mechanics of stealth games such as Metal Gear Solid, in which the area which is seen by various NPCs, various characters in the game, is very important and helps to create the game experience. I wanted to tell you one more thing. It's a concept that I mentioned 2 weeks ago, but didn't elaborate on it. This concept is called window of perception. What is a window of perception? If you think about any kind of intelligent behavior, this intelligent behavior is a process. So, for example, a process might be like a guard in a dark room can hear a noise. Okay, what it is supposed to do? The guard should or could, could head to the switch light to switch the light on to find out what's happening, what's the source of the noise. Okay, and this is what you would expect from a real person in the real world. Right, so this is a process. A guard hears something, goes to the switch, switches the lights on, checks for the noise. Okay, but this is some kind of a process which takes some time. Okay, it's a reasonably nice, reasonably intelligent behavior. But now imagine that in most cases, here, navigating through the game world, we'll see this agent just for a moment. Okay, and what can be perception of the player in this situation? The perception may be there is a guard in the room. Okay, he heard some noise which perhaps I created, so he heads in opposite direction and disappears. End of the story. What? Stupid agent, some kind of a glitch. It should come close to me and discover what was the reason of the noise. If I stayed there any longer, I would spot the guard coming to the switch light, switching the lights on, and putting me in a much worse situation. But by that time, I managed to escape, and I'm not in the room anymore. Okay. The way in we perceive the intelligence may depend on the time we have to observe the character. And once again, it is a confirmation of my thesis given to you 2 weeks ago, that simple things often look good. All right, simple things is a quick guard who just takes his gun and shoots at every noise, every trace of presence of potential enemy. Okay, and you will always say, okay, it's at least fast, right? Maybe not very intelligent, but at least you will have an opportunity to observe his intelligence. Okay, and too complicated intelligence can lead to problems because you can have too short window of perception. In this case, this is the player's perception of the agent to tell whether the agent demonstrated intelligent behavior or glitchy behavior. Okay, and I will give you another example. Imagine you enter the same room, there is the same guard there. You create a noise. You expect that the guard would go to the switch to switch the light on, and he doesn't. Okay, he just tries to find in the darkness what was the reason for this noise. And then you think, oh, how a stupid AI. Okay, why didn't he switch the lights on? Actually, the question that I asked so many times watching horror movies, why the hero is not switching the lights? Electricity is off, but yes, this might be the case. What if a very intelligent guard, a very intelligent autonomous agent in the game already knows that the electricity is broken down in this room, so there's no point to switch the lights on, and the only thing is that the agent has to find out what's going on in darkness. Or I will give you another example. It's a very intelligent collaborative agent who has a friend, and this friend left the room a few minutes before, to collect cigarettes from another, room where they stored cigarettes. Okay, so when the guard heard the noise, he was thinking that it was his friend coming back with the cigarettes, not an enemy. Right? So he didn't react. But if you know that, if you can stay in the game, observe this guard for a longer time, you will say, wow, what a beautiful, wonderful, deep, smart AI in this game. But if you just spotted, oh, a guard, oh, he didn't move, that's stupid, some glitch, started. Low quality AI, right? So high quality AI may quite often be considered low quality AI because of the window of perception problem. And that's one of the main reasons why eventually in many games, developers eventually accept simpler solutions rather than more sophisticated. All right. So today we'll be looking into a very simple solution, so-called line of sight test. So, of course, I'm following here a very simple pattern. So, if you have a guy in a hat and a young girl with golden locks, of course, our hero is the girl, and the guy here is the enemy. All right, and the enemy will shoot at the moment he spots the girl. Okay, but okay, so this is the situation in which the enemy will definitely shoot because he can see the girl, and this red line symbolizes line of sight. We know that, of course, in physics, the light is a wave, electromagnetic wave, and there is no such thing like line of sight. But if we imagine that everything that I can see means that there is a line between my eyes and this object that I can see, and it's this line is unobstructed, that's line of sight, of course. And if there is, it's not a toast, it's a wall. Okay? If there is some kind of a wall in between them, then there is no line of sight, and the guy cannot cannot shoot the girl. Okay. Now, what's important is not this wall you may like or you may hate my graphics here, but this is just a representation of something for which the important part is this thing. Okay. So the blue line is the obstruction, and the red line of sight. And what we need is a mathematical test. And because we will be programming this in GFC, so don't think that it will be easy, all right? It will, because I will give you a code in a moment, so it's like copy and paste. But it has to be programmed, all right? GFC does not offer any tools to check the line of sight test. You have started programming in Unity already, yeah? Have you done raycasts already? No? This is the basic raycast technology, which I'm sure Darren will teach you very, very soon, okay? And I'm sure that some of you already have already done this. But we will be doing this from scratch because there is no raycast in GFC, so you will have to program it. Line of test. Basically, line of test can be reduced to line segment intersection. So we have two lines, AB and CD. It's important to note that these are segments. So a segment in geometry is defined as a set of all points lying on the closest connection between two given points. All right, but basically it's just a line from A to B and another line from C to D. And now, if these two line segments intersect in any place, this means that the line of sight test is failed, is negative. Negative means the guy cannot see the girl, okay? If they don't intersect, this means that the guy can see the girl, okay? And here we have some maths. I think that after experience last year, this math shouldn't be very difficult for you. But also I want to keep your attention, so I won't comment on the content of this maths. It works, okay? And if you have the mathematician spirits, check this, read this code, and you will discover how it works. And not particularly complicated. For general use, I will just explain this from the point of view of using, all right? Basically, probably, in most cases, when you find a problem in your game programming, you will go and you will find a piece of code, right? And someone who would, if you paste this code to your program, it will work, it will discover the line of sight test, okay? Basically, this is solved on the basis of vector algebra. And now this function takes functions a, b, and d, and considers that AB defines one segment, CD defines another segment, and then returns two coefficients, K1 and K2. And we did, now I remember, we did a very similar thing when we considered the task of intersecting a line with a rectangle with collision detection, okay? Because this is actually a kind of collision detection, but this time we need to find a collision between two linear segments. All right, not rectangles, not anything more substantial. So that's line of sight test. The result K1 and K2 will provide you where the intersection point lies within the segment. So K1 will return 0 if the intersection point is at the position A, and will return 1 if the intersection point is at the position B, and it will return 0.5 if it is right in the middle, or 0.2 if it is somewhere here. For this situation, it will probably return something like 0.4 because the intersection is nearly at halfway between A and B. This K1 can be used if you have a task in which you not only have to discover whether there was an intersection of the segments, but also where this intersection was, okay? So if we had a situation like this, then K1 coefficient would be equal to 0. If we had a situation like this, K1 would be 1. And in this case, it is basically somewhere between 0 and 1. Value between 0 and 1 means, yes, there is an intersection, or at least maybe there is an intersection because it's not yet everything, all right? If the value would be less than 0 or greater than 1, this would mean that the CD segment would be completely out of the scope, out of the range of AB. So if K1 is less than 0, this means that this line would be somewhere greater than 0, somewhere on the right, absolutely no intersection, okay? So the visibility would be unobstructed, all right? Yeah, and here you can see the range for K1 less than 0 and greater than 1. For the proper segment intersection, you have to check both coefficients, K1 and K2. So K1 must be greater or equal to 0, and less or equal to 1, and the same with K2 has to be greater or equal to 0, or less than or equal 1. So we can actually have a simpler version of this function, which is maybe not so flexible, but easier to use if the only thing we want from this function is to test the line of sight, okay? Provide points A, B, C, D, right? But now all the calculation is done internally, and the function returns true if the line segments intersect, or false if they don't intersect. So once again, to remind you why we are doing this, AB is line of sight between guard and the player, okay, and CD is the obstacle. If they intersect, this means that the guard the guard cannot see the player, but if they don't intersect, there is a line of sight and the guard can see the player. But now, this is a wall, right? And if this guy would be standing here, okay, he wouldn't be obstructed by this line, but by this line, all right? So how to create, how many lines we need for the wall, which is not just a line, walls are thick, okay? So we have to take into consideration the thickness of this wall, the entire size of this obstacle. So how exactly represent the obstacle? Generate the CD. First of all, there are various solutions here. You can find hardwire borders. So you can take the map that you use and just line all the lines so that to get, you know, get all possible expected obstacles into consideration, and you just then test against a set of lines. Fortunately, this line of sight test is very effective. It's very light. There are no complicated calculations in it, so you can repeat it for many lines in your scene. You could consider using all edges, okay, and this will work for all convex polygons. If you have a number of edges like here, 4 edges per wall, it will work, okay? But actually, it's a simpler solution, diagonals, okay? If the site is obstructed by diagonal, it will be obstructed by the wall and the other way around. If it is obstructed in any way by the wall, it will be also obstructed by diagonals. Okay, so this is probably the best solution because you can easily generate, if you know about your obstacles, you can easily generate all the diagonals and then test against each diagonal. So 2 tests per rectangle, and you have everything done, okay? Another thing, this is the line of visibility, but, you know, I can see you now, but I can see you now, right? I don't have eyes in the back of my head. So line of sight is one thing. And then we have so-called visibility cone. Visibility cone is attached to your favorite thing in games development, the velocity vector. Okay, I told you last year that we will never escape from vectors, and particularly from velocity vectors, because we generally accept the fact. It's a little bit simplification because you could walk like this. Okay. You could look around. So with looking around, you would need another vector based on the velocity vector, the look at vector. Okay, so you could look right, look left, look even a little bit backwards. All right. But in the simplest situation, we can base the visibility cone on the velocity vector and say that some area to the left and some area to the right from the visibility vector is your visibility cone. So the area in which you can spot the player or the enemy, okay? And now, question to you. Please don't pick to the next slide. Do you remember what we did last year in maths classes to find out, for example, if something is on your left or your right or in front of you or behind you? Yes? Yes, dot product, yeah? That's what you meant. Dot products and cross products, exactly. Dot product can tell you whether something is in your front Okay, and we did a very simple test. For an object to be in your front, the dot product between your velocity vector and the vector connecting you to the enemy. You will play as my enemy now, okay? So that's the vector to the enemy, that's my velocity vector or forward vector, okay? Forward enemy vector dot product. If it is positive, this means that it is in my front. If it is negative, this means it's behind me. But if the enemy is exactly in front of me, then the dot product will be 1. Okay, and if both vectors are normalized, actually the value of this dot product will be the sine of the angle. The sine of the angle between my forward direction or velocity direction and the vector to the enemy. Because usually visibility cone is narrower than just in front of me, okay? I can assume that if the enemy is somewhere there, even if it is formally in front of me, I won't see it, okay? So let's say that it would be perhaps 30 degrees to the right, 30 degrees to the left, creating a nice visibility cone. And in this way, we get a nice path. We take a vector, which is the player current position, minus the guard position. And this is this line of sight or direction, or simply enemy vector, okay? Where is my enemy? Or in this case, because I am the enemy, we equip the enemy with intelligence. So the enemy is looking for the player. So it's the player direction vector. Yes, that's what it is. And we calculate the dot product of normalized velocity vector and normalized player direction vector. And if it is less than 0.5, and by the way, a sine of 30 degrees is 0.5. So this will mean that the angle between two vectors is less than 30 degrees, whatever side it is, okay? Because fortunately, very fortunately, and I'm talking stupid things, it's a dot product, so it's cosine, not sine, sorry, cosine. Indeed, a visibility cone that would be just 30 degrees here and 30 degrees here would mean that the guard should definitely visit his optician, because he has a big problem with marginal vision, okay? So no, our visibility cone is not 30 degrees left and right, it's 60 degrees left and right. And indeed, cosine of 60 degrees is 0.5, okay? And cosine is symmetrical, okay? So a cosine of 60 degrees is 0.5. And cosine of minus 60, of negative 60 degrees is also 0.5. So it works. 0.5 or more means that the object is no more than 60, sorry, not 30, 60 degrees away from my front direction, okay? A very nice visibility cone, okay? And these are two aspects that should be implemented to get autonomous agent who can sense its environment, not cheating, but spotting what it is supposed to spot.